Uh, Thank you for giving me the opportunity to speak to you guys today. I'm really excited to talk to you about some work that we've been doing at UC Santa Barbara with my colleagues listed over there. There's quite a few of us. It's a big project. And I want to draw your attention to two blue names over there that were both high schoolers when this project started. So I don't know how often high schoolers get published in top tier venues, but this is one of them. So this work is not, this work is about two things. It's about binaries, and it is about offensive techniques on binaries, so attacking these binaries. We want to find vulnerabilities in the binaries, and we want to exploit those vulnerabilities, and we really want to understand how the current state of the art lends itself toward these approaches. And our motivations are twofold. One is we're really interested in the current state of the art. We're interested in what are the limitations of current offensive binary analysis techniques, where they can be improved. And this is very relevant because right now we're experiencing an explosion of binary code. Of course, high-level languages have always compiled down to binary, and you have to run binary in your CPU at some point, but now we're having this IoT renaissance where everything is a smart device, and these smart devices often run binary firmware and often run multiple different binary firmware images on different sub-devices. So we have a lot of binary code that can now be attacked, and we need to understand how current techniques are at identifying and exploiting these vulnerabilities. And DARPA has recognized this need and created the DARPA Cyber Grant Challenge. It's a competition for an automated binary analysis framework and binary exploitation framework. They put a lot of money on the table, which of course is also a good motivator. But this is their statement that this is important, right? And so we approached the idea of analyzing binary, offensive binary techniques from our standard scientific perspective. In science, we look at existing work in the field, use it to get some idea of how to improve it, and output some new work back to the community. And we did the same thing. We looked at existing binary analysis techniques. And then we kind of hit a interesting problem in that these existing binary analysis techniques, the ones that publish source code so that you can build off of them, and the ones that publish enough of an idea that you can build off of it, the release tools have some problems, right? And so there's a set of these problems. One is that sometimes even if the tool is published, it's not open source. So it's very hard to build off of it. Even when it is open source, sometimes it's basically not open source. So if you write your tool in a language that is extremely hard to use and extend, like sometimes happens in our field, it's very hard to build something off of it. Even when they are open source, they're often very inflexible, or they lack support for multiple architectures. So they're very architecture dependent. And if you're interested in analyzing firmware, x86 doesn't cut it. Even x86 and ARM alone doesn't cut it. You need a very wide support of architectures. And these tools are not composable. They're also probably not compostable either. But they're definitely not composable in a very easy way, because if they're not really made to build off of each other and extend each other, it's hard to combine them. So you have symbolic execution and you have some static analysis, and combining these different tools from different papers is non-trivial and sometimes impossible. And this is a problem for two reasons. One is that it is hard to understand what the real impact of the work was, right? How much did the work really improve over the previous state of the art versus how much it has just a different implementation and happens to get different results. So it's hard to compare these things on an equal footing because all the tools are implemented very differently. And it's very hard to build off of, because if you want to combine multiple approaches to create the next generation of binary analysis, it's tricky if you don't have a solid footing that can support all of your what you want to do. So we had the idea of making a binary analysis framework that solves these problems, that allows us to explore in a very systematized way how different analyses fit together, how symbolic execution can assist static analysis, how fuzzing can get looped into the whole thing, and what effects this has, right? So we're really trying to systematize the field of binary analysis so that we can have a standard base on which we can create approaches, compare them, and see what happens and how well they work. So this binary analysis framework we released and made is called Anger, and this is the framework on which we did this study, this survey of offensive binary analysis techniques. And Anger is extremely modular. It's made to be composable and probably compostable as well. And it's made out of modules that fit together and are very configurable. You can take these modules, you can split them apart, mix them together, and really build different types of analyses. So you might combine different modules to create dynamic symbolic execution engine that uses value set analysis to resolve bounds on symbolic variables. You might have a static analysis system that also uses concolic tracing to try to prove that the detections are not false positives. You could have a concolic tracing engine and integrate it with another tool, because Anger is very flexible. It's meant to be used as a library. So you can integrate, for example, a fuzzer to understand how symbolically assisted fuzzing compares to just normal symbolic execution. And all of this is on a single base, so it's really comparable. So I want to really stress this, because if you have different implementations of different techniques, it's very hard to tell if the improvement was from the implementation or from the technique. With Anger, with this work, you can really look at it on a single implementation and say, OK, that theoretical advance really did this to the results. And so I mentioned Anger has a couple of different modules. It has a bunch, and I don't have time to go into all of them here, but I'll go into an overview of modules that are also useful outside of Anger as kind of a general toolkit in binary analysis. So we created a binary loader, which allows an analyst to look at a binary and get a view of how it would look in memory if it's loaded. It's a non-trivial process, and our binary loader supports ELF binaries, Windows binaries, CyberGrant challenge binaries, and all sorts of binaries that IDA supports, because it could use IDA as a backend to load them as well. This is very useful. We see a lot of people using this outside of Anger. We also created a Python wrapper for libvex. We use vex as the intermediate language in Anger, allowing us to support many different architectures. We see this being used in the community as well, a lot in research, actually, over the last couple of years. And we created a really useful module that abstracts data model domains, right? So you have symbolic variables in symbolic execution, and you have value sets and strided intervals in value set analysis. And we have a module that allows us to abstract these into a common representation, basically an intermediate representation for data domains, which really allows us to compose these different analyses, because we can switch from symbolic execution to value set analysis on the fly as needed. So we have all of these cool things. So what did we do with them? Well, we did many things. One of them is this study on how well current binary analysis techniques and offensive binary analysis techniques work on the CyberGrant challenge, right? So if you had a research lab like ours and you wanted to participate in the CGC, could you use existing techniques to basically really apply them in kind of this real world-like setting? And to participate in the CGC, you need to do two things. You need to analyze binaries, and you need to exploit these binaries. You also need to patch binaries, but here we're focusing on the offensive techniques. So we did a survey of the existing works, the existing work that we wanted to systematize in this project, and we picked out these kind of core papers. They cover everything from binary analysis for vulnerability discovery to automatic exploit generation to automatic exploit hardening against software mitigation techniques, software vulnerability mitigation techniques. And there's actually a bunch more papers, of course, that we've drawn. These are kind of the core ones. And we implemented a lot of different analyses to evaluate, right? Everything from kind of these base analyses like a control flow graph recovery through symbolic execution with various different optimizations that we can combine and compare and contrast on a similar implementation base. We implemented a lot of static analyses, such as value set analysis, and we tested how well it interacts with fuzzing. If you have symbolically assisted fuzzer, we looked into crash replaying, a lot of this sort of stuff, and we invite you to read in the paper how we designed and implemented this on a common base in Anger. So, of course, we evaluated all of these analyses and compared how they fare against each other. And our data set was 131 binaries that DARPA released as the qualification event for the Cyber Grand Challenge. And these binaries are really interesting from a research perspective because they're very diverse. They have different authors. Their sizes are everything from a couple of kilobytes to 10 megabytes. 10 megabytes is roughly the size of QEMU, I believe. So that's a fairly beefy binary. They have a lot of different types of vulnerabilities, everything from null pointer dereferences to function point overwrites, vtable trickery, all sorts of really subtle vulnerabilities and some obvious vulnerabilities. And they provide a ground truth. So we can really say, hey, this detection we found, how many false positives did this tool create? So was this detection a false positive? Or did we find all of the bugs? And of course, we'd never find all of the bugs, but we can try. And the binaries are simple in a way that allows us to save on implementation time in the way that they interact with a very simplified environment model of the operating system. So we implemented all of these techniques and ran them on all of these binaries, and we found some interesting results. So for one thing, we found that in our data set, our fuzzer that we kind of used as a control check of offensive binary analysis found almost 3 times as many vulnerabilities as basically any other single technique, and it found more than the union of the rest of them combined. Right? So this is very interesting. We used AFL as our fuzzer, and AFL, it turns out, is extremely good. So it would be interesting to further look into why our results differ from Lava's results in this sense. But we looked into why on our binaries fuzzing was king. And it turns out that this is because in the CGC binaries, at least, most of the crashing conditions occurred about 10,000 basic blocks into, or 100,000 basic blocks into the execution of the application, right? And fuzzing found those. And symbolic execution, before reaching those, tends to suffer a state explosion. So symbolic execution, like Tim said earlier, suffers from this inability to penetrate very deep into an application. But on these binaries, we didn't see fuzzing having the same problem. Fuzzing actually got fairly deep. This is also actually symbolically assisted fuzzing, so that might also explain why it was able to penetrate deeper. But fuzzing alone also did pretty comparably. So we did this study. We implemented this tool upon which the next generation of binary analysis can be built, and so we open sourced it. So now we hope to provide a base for future binary analysis research. The code is on GitHub. You can grab it right now. Actually, there's a Docker image that you can just run with your scripts, and it'll execute them in Anger. There's documentation. There's an IRC channel. So we really want to push this as a tool in the toolbox of security researchers. Feel free to ask us for help. We're very responsive and really excited for the next generation of binary analysis. Anger was built by a very large team. This is all of us from UCSB that have worked on Anger in some capacity. And there's more people that are external collaborators, and it's really a fairly serious project that we're pushing forward. And with that, I would like to open it up for any questions you guys might have.
All right. Any questions? So while we're waiting, I think one of the benefits of having this extensive study on the same platform is quite a good plus. So the question would be, when you implemented all these different approaches in the same single platform, did you do any additional testing to prove that the algorithm that was presented by so-and-so is indeed reflected correctly on my test bed?
It's a tough problem because a lot of these papers have very targeted evaluations.
Yes, that's the reason.
Yeah. So for example, there are papers that target the state explosion problem, right? And they have a motivating example, and then they show that they work on the motivating example. Mm-hmm. And we work on the motivating example.
Yes.
Past that, it's hard to analyze it further, right? We feel we implemented this correctly. It works like it says in the paper, but does it really work the same as the original implementation? For open source ones, you can check, but a lot of these things aren't open source, and or the tools are just plain not available.
Right. Yeah.
So for those, you can't really check. We've done a lot of applications of Anger. Let's see. Oh, no, mine got disabled. We've done a lot of applications on Anger in terms of, of course, research on what we feel should be solvable with these techniques, but also in the CGC and in capture the flag competitions. Mm-hmm. Actually, last weekend at DEF CON, Anger got first blood on the top reversing challenge at DEF CON. So that's against human hackers. And we feel that from our results, it makes sense. When we see that, hey, there's a path explosion here, we look into it, okay, that makes sense. When there are something doesn't find a binary crash, we look into the binary and see, okay, well, from a theoretical perspective, this would overwhelm this analysis and that would overwhelm that analysis. Okay. But kind of we do what we can with the openness that is available.
Yeah, I totally understand. Thank you for the detailed answer.